We present TokenHMR, a method for estimating 3D human body pose and shape from a single RGB image. While our goal is to obtain accurate 3D human pose and shape, for many applications it would also be good to have an accurate alignment between the projected 3D body and the image features. We observe that, with today's methods, you can't have both. The more accurate the 2D fit, the worse the 3D pose, and vice versa. We performed several experiments to explore and quantify this issue, which is caused by a mismatch between the simplified camera model assumed by current HMR methods and the true camera. This mismatch manifests itself in two ways. First, the pseudo-ground-truth data used to train most methods is computed using an optimization method. This method also has a mismatch between the assumed camera and the real camera. This results in biased ground truth. For example, to account for the effect of foreshortening, people are often tilted or their legs are incorrectly bent. Second, the loss functions used to train HMR methods balance 3D and 2D error terms. The 2D term minimizes the error between observed and projected joints. When the camera model is wrong, the network learns to distort the body to fit 2D features. We quantitatively analyze the impact of this problem using the synthetic dataset, Bedlam, which has perfect ground truth and known cameras. First, we analyze the predicted bodies from HMR 2.0. Then we take the ground truth 3D pose and project them into the image using the camera model from HMR 2.0. We then compute the common 2D error measure, the percentage of correct keypoints, or PCK. This defines an upper bound on how good a method can be on the PCK metric if it obtains perfect 3D pose estimates. We then evaluate the PCK of HMR 2.0, which is a state-of-the-art method. It turns out that the PCK of HMR 2.0's predictions is higher than that of the ground truth. This means that HMR 2.0 and other similar methods overfit to the 2D data at the expense of 3D accuracy. We also observe that the converse is true. Accurate 2D fits can produce grossly wrong 3D poses. For a given PCK level, there are effectively an infinite number of 3D poses that can produce this. The solution to this would be to use the correct camera for the given image. Estimating the true camera from a single image, however, is a highly ill-posed and unsolved problem. To address this issue with today's technology, we introduced TokenHMR with two synergistic methods that improves accuracy. Our key insight is that, while closely fitting 2D image evidence and 3D pseudo-ground-truth introduces camera and pose bias, loosely fitting them is still valuable for correcting grossly incorrect predictions. That is, we should use these to get the pose roughly right, but not rely on them for fine pose detail. What is important is to find the proper joint-specific loss thresholds, above which the 2D evidence can be effectively used. Hence, we define a new loss function called TALS, which stands for Threshold Adaptive Loss Scaling. It penalizes large 2D errors, but only minimally penalizes small errors. However, this creates a new problem. Within an error tolerance, there are many valid 3D poses. Which one should we prefer? For this, we need a prior that prefers valid human poses over invalid ones. Unfortunately, existing priors based on Gaussian mixture models or variational autoencoders are biased towards frequently occurring poses. What we need is an unbiased prior that restricts the network to only output valid poses. This brings us to the second key component of TokenHMR, the pose tokenization. We convert the problem of continuous pose regression into token prediction by first tokenizing the space of human poses. To that end, we use a vector quantized VAE to convert continuous poses into a discrete representation called tokens. We use 3D poses from Amass and Moyo to train our tokenizing network. TokenHMR uses the pre-trained tokenizer, which provides a vocabulary of valid poses. Note that unlike previous priors, our approach effectively provides a uniform prior over valid poses. Finally, we put the two components together. Our new tails loss forces the model not to overfit to 2D keypoints and pseudo-ground-truth data, while the tokenization keeps the network from distorting the 3D pose. We extensively evaluate TokenHMR and other recent methods on the EMDB and 3DPW datasets, which contain high-quality 3D ground truth. Using the same data and backbone architecture, TokenHMR exhibits a 7.6% reduction in 3D error on challenging EMDB datasets compared with HMR 2.0. Here are some qualitative results. Note how the 3D pose of TokenHMR is more plausible than HMR 2.0. In conclusion, we present TokenHMR, a novel approach to 3D human pose estimation from single images. We have two main contributions. We introduce a new paradigm of pose estimation based on estimating a discrete tokenized pose representation. Along with that, we formulate a new loss called TALS that mitigates some of the bias caused by having the wrong camera projection model. The code and models will be available for research. Thank you for watching.